Like to do as a student was I'd like to look at other books, also look at how other authors define things and the types of problems that they show. And so I'd look for more examples. I don't like to focus on one example and that's it, because I don't like to spend too much time on one particular example if I'm trying to learn something new. I want to see a lot of different examples. So one of the things you could do is you could go to this chapter 19. Chapter 19, the reason I don't cover it right away is because it deals with batteries, and I don't want to talk about batteries at this time. But, you know, when the way a battery operates is by taking advantage of redox reactions. And so we can see here, you can see the two types of redox reactions you're going to have. One type of redox reaction is you have to predict products. So here, like for example, in this particular redox reaction here, how would you tackle this particular problem?
First the inventory, then seeing the charge something would have.
Yeah, inventory, yes, for sure. You do inventory and then you...
After inventory, you will write the half reactions.
Yeah, you look at the chart, you know. For example, bromine and iodide, those are both species on the chart. Nickel 2 is not on our chart, but it's on this chart here, cadmium. You know, these species are going to be on the chart. H plus, bromide, chlorine, iron, NO, water, iron 2, H plus, magnesium. All those species are on the chart. And so we can get the half reactions from the chart. I had a question about this earlier. Not everything's going to be on the chart. You know, was I talking about that carbon monoxide poisoning thing yesterday?
Yeah.
You know, it's not everything, and not only that, when it's on the chart, we make certain assumptions. Like, for example, when we use this chart, there's a little footnote there. The footnote says that the concentrations are going to be 1 big M, which is 1 mole per liter, and that the gases are going to be at 1 atmosphere or 1 bar, you know. And so there's certain assumptions, but when and the temperature is room temperature, which is 25 degrees C, but when you start changing those things, then you can get other things, other reactions that can take place. And so sometimes it's kind of complicated to predict what's going to happen, and so you just try it and see what happens. So the other type of problem is, you know, for example, is thiosulfate on the chart? No. And so what they did was they just threw this in. But the chlorine, is that on the chart? Yeah, so chlorine to chloride, that's on the chart. We just copy that down from the chart. But thiosulfate, they saw what happened. Okay, they mixed it with chlorine. Well, thiosulfate's a known reducing agent. And it's a pretty good reducing agent. So they mix it with chlorine and they see that the thiosulfate converted to, what's that? Sulfate. So thiosulfate was converted into sulfate. Is that half reaction on the chart? No, this half reaction is not on the chart. And so if the half reaction is missing, at least we know what happens. Thiosulfate got converted to sulfate, so that's key to know. But since the half reaction is not on the chart, we have to figure out what that half reaction is. We did a problem just like this. Do you recall a problem that was just like this? The problem that was just like this was, and so these are the types of connections you can make if you look at these things a lot. The type of problem that was just like this was ethanol. You know, if I have ethanol in wine, what does it get converted to? Well, it got converted to what? Vinegar, acetic acid. And so under those conditions, normally when you oxidize ethanol, you're going to oxidize it to CO2, but in this case it was partially oxidized to vinegar. And so on one hand, we have ethanol going to vinegar, and then oxygen was the oxidized. Well, oxygen's on the chart. And so one species is on the chart, the other is not on the chart. So we had this thing, this kind of composite type deal that we had. And so we need to use the method that we talked about, balance. So we separate this out. You know, the chlorine we could separate out because this chlorine plus 2 electrons yields 2 chloride. Thiosulfate goes to sulfate. We balance all elements other than oxygen and hydrogen, and then balance out the oxygens, and balance out the hydrogens, and balance out the charge, and then we get the half reaction there. I don't know if they went through all the steps here. Let's see if they did. They didn't go through all the steps. They skipped it. And eventually, this one we just copy off the chart. This one you balance using the technique adding waters and adding H plus and adding electrons. Balance. Zinc goes to Zn2 plus, that's on the chart. Zinc goes to Zn2 plus 2 electrons. We just copy it off the chart. This is not on the chart. This is Sb2O5 goes to SbO plus, not on the chart. So we'd have to use the same method, you know, of balancing. Nitrate goes to NO2. Nitrate goes to NO2 is not on the chart. You know what's on the chart? Nitrate goes to NO. But nitrate goes to NO2 is not on our chart. It's on some other charts. I think it might be on that chart there. And so we might have to do two. We might have to go tin goes to this, and nitrate goes to NO2 as two separate half reactions, and balance those out.
Is there going to be anything that's not on our chart?
I'm sorry?
Test?
Is there going to be something not on the chart?
Yeah.
On the test, potentially, yeah. You know, there's going to be. It could very well be. And so this is the half reaction for nitrate goes to NO2. You know, we add the waters, we add the H plus, and we add the electrons. For tin, it goes to this. We add the waters, we add the H plus, we add the electrons. Then add them together. Nickel 2 goes to NiO2, nickel 4 oxide, that's not on our chart. But tin 2 goes to tin, that's on our chart. You know what this is? Oh, if there's an R here, it would be chromate. It's oxalate. This would be oxalate goes to CO2, not on our chart, so we'll have to figure it out. Permanganate goes to manganese 2, on our chart. We just copy it right off the chart. And so permanganate goes to manganese 2, you copy it right off the chart, it would actually be, we doubled it, but it'd be permanganate plus 8H plus 5 electrons yields manganese 2 plus 4 waters, and then they doubled it. The oxalate goes to CO2 is not on our chart, we have to balance that separately when we add them up. Chloride goes to chlorate. Is that on our chart? Chloride goes to chlorate on the chart? No. So we'll have to do that separately. Chloride goes to chlorate, add waters, add H plus, add electrons. Nitrate goes to NO. Is that on our chart? Nitrate goes to NO. Is that on our chart? Yes, it is on our chart. You see how a huge advantage having familiarity with the chart is going to be on time tests. It's going to be a huge advantage. Because other people are just struggling and just to get started. When you go, oh, I've seen that before. You know, if you've seen it before, it's easier than if you've never seen it. And so this is why getting a broad range of exposure, you know, so you've seen a lot of things before is always good practice, I think. So I have a different philosophy. Some instructors here, they say, you know, if you don't face the challenge, a rigorous challenge, like if you don't spend hours on a particular problem, working it out and figuring it out yourself, you're not learning. But my philosophy is a little bit different. I don't think spending hours. I mean, it's great if you get it. But anyway. So, myself, okay, so we have the chart method, and then we have this composite method where, you know, we're told what happens. We're told what happens. Nitrate goes to NO, that's easy, we copy it off the chart. Nitrate plus 4H plus 3 electrons goes to NO plus 2 waters. Chloride goes to chlorate. I don't know what that's gonna be, but it's gonna be chloride plus 3 waters, plus, we just figure it out. None of these are on the chart, so we have to do these separate. Dichromate to this is one, and then ammonium to nitrogen is another. Sulfate goes to sulfur dioxide. Is that on our chart? I think the answer is yes. But, can't remember. I know there's sulfate on our chart, but does it go to sulfur dioxide? Yeah. Okay, then we're good. We could copy it. It's not like I have it memorized. It's just like, oh, I remember seeing that before. That's all. And so it saves you time, because if you don't have to balance it, like for example this, we'd have to balance it. But if you could just copy it off the chart, it saves you a lot of time. Here again, nitrate to NO, just copy it off the chart. This one we can't. The zinc we can't, the lead we can't. Were there any other types of combustion reactions? Yeah, there were. What were they? There was single replacement and double replacement is not combustion. Redox. Double replacement. Metathesis. There was single replacement and acid base is not redox. Acid base is the oxidation states in acid base reactions don't change. So it's not redox. We're just focusing on redox for this test. It would be combustion. And so that would be it. The combustion, that's what even there it's hard to predict. Under complete combustion, we predict will form CO2. Okay. Any other questions? Let's get some more practice with Lewis structures. What did we leave off yesterday? Third, bromate, BrO3 minus. BrO3 minus, bromate. All right, this one it's best to follow the steps. So let's take a look at the steps again. Count the total number of valence electrons just for charge. How many valence electrons does bromine have? 7. 3 oxygens is 3 times 6 electrons. 18. And then the -1 charge. -1 charge, we have to add 1 electron. The electron's negatively charged. So this gives us 26 electrons. Then we have to draw out a structure. Call this the tentative structure. So we want to just bond all the atoms together. One of the things to avoid, we want to avoid forming oxygen, oxygen, oxygen chains. sometimes it's not possible to avoid it, but if it's possible, avoid it because oxygen chains are unstable. Like a 3 oxygen chain would be ozone, O3. Ozone's pretty unstable, pretty reactive chemically. 2 oxygen chain with single bonds like that would be hydrogen peroxide. It's unstable. Peroxide. So we try to avoid that kind of thing. And so what we're going to do is we'll put the bromine here and then have all the oxygens attached to the bromine like this. Where we don't have any chains of oxygens. And then we're going to complete the octets. We'll complete the octets here. Bromine is going to need just another pair. That's complete. So how many electrons have we used up here? We count them 2, 4, 6, 8 times 3 is 24 plus 2 is 26. 26 electrons. We used up 26 electrons and 26 electrons here. And so that takes care of step 4. Calculate the number of electrons in the structure and compare to the actual. They match. So we don't have to do check to make sure. Step 5 is check to make sure there's octets and duets. Everybody has an octet, so everybody should be happy, right? If everybody has an octet. But I added a step 6. What's step 6? There's one more thing we do for those structures. Anybody remember? If we're doing like double bonds, then we have resonance forms. But in this case, we aren't doing any double bond. We can move this lone pair, like for example here or here, but we aren't going to do that. It's just going to stay like this. Normally what we do is we fix the atoms in position and then move the electrons around, but this is not really showing the shape, the actual shape of it. So we'll just leave it like this. There's something else we calculate. In addition to looking at the octets, the total number of surrounding each, like this oxygen has an octet 2, 4, 6, 8. This bromine has an octet 2, 4, 6, 8. All these have an octet. In addition to looking at the octet, there are 3 ways of counting electrons. What were the 3 ways of counting electrons? There's the octet, there's the formal charge, and there's the oxidation state. So what we typically do with Lewis structures is we always calculate the formal charge. Whenever we draw a Lewis structure, we also determine its formal charge. And so what are the formal charges here? Like for example, this oxygen, what's the formal charge on that oxygen? Negative. And these oxygens all look the same. You see, so all these oxygens are negative. There's 2, 4, 6, 7 electrons. Oxygen should have 6. How about bromine? What's the formal charge on bromine? It's +2. It's kind of high. 2, 3, 4, 5. Bromine should have 7, like fluorine. So those are the formal charges. And then when we add up the formal charges, we get the net charge. So we put square brackets around here and then add them up. So +2 minus 1 minus 1 minus 1 is going to give us -1 for the charge. And so this is a good structure because the octet rule checks out. We got octets on everything. But it's not so great because the formal charge is not minimized. What this shows is that essentially bromine lost 2 electrons. Those electrons went to the oxygen. The bromine came out short 2 electrons. So what can happen is, this is going to be versus this. What can happen sometimes is you can get more than an octet. You can get something called an expanded octet. Expanded octets, there are different reasons why you might expand the octet. So let's talk about expanded octets. So this is the bottom part here. Molecules with more than 4 electron pairs. 4 electron pairs is 8 electrons. So molecules with more than an octet around the central atom. There are 2 main reasons to do this. One reason is to increase the number of bonds. The more bonds, typically the more stable it is. So for example, phosphorus. Phosphorus has 5 valence electrons. If it uses all 5 valence electrons to form bonds, then we can get 5 bonds. If we get 5 bonds, that's 10 electrons. So that's more than an octet. And so one reason is to increase the number of bonds. Sulfur, how many valence electrons does sulfur have? 6. Sulfur has 6. So if it forms 6 bonds, the more bonds, the merrier. The more bonds, the more stable. And so sulfur can expand its octet. In this case, I mean, it's 2, 4, 6, 8, 10, 12 electrons. It's a lot. However, this only happens for 3rd period and higher. And so atoms with 3rd period and higher, meaning 4th period, 5th period, that is 3rd shell, 4th shell, 5th shell. These are big atoms, and they can do that. Atoms in the 2nd shell cannot do it. 2nd shell, and so expanded octet is greater than equal to the 3rd shell, or 3rd period. And so one reason for doing this is to also reduce the formal charges. And so we can say formal charge, we can minimize it. And so the example here would be this. Bromine's short electron density. So what we can do is we can have oxygen form a double bond, and it's not going to screw up anybody's octet. So for example, if we double bond here, like this, then oxygen still has an octet, and bromine still has an octet. But what happened to the formal charge? Well, if you look at oxygen's formal charge, what is it now? It went from -1 to 0. And if we do that again, let's take this one here. And so let's take this electron pair and form a double bond here. We aren't going to do it again because that will screw it up. If we did it again here, then this oxygen goes to 0. And so what are the formal charges now here? Formal charges would be 0, 0, and for bromine it would be 0. So all the formal charges are 0, except this one, this oxygen. There's got to be at least one negative charge here. So if I made another double bond here, then that negative charge would go to bromine. If I keep this a single bond, then the negative charge goes to oxygen. Which one wants the electron more, bromine or oxygen? Which one wants the electron more, bromine or oxygen?
Oxygen.
How can you tell?
Because bromine has 7 electrons usually, so it's more stable.
Possibly that's one way, but it's not. Like for example, iodine. Iodine has 7 valence electrons, but it wants the electrons less than oxygen. And so the way we can tell which one wants it more is by this. What is this called? electronegativity. So oxygen is more electronegative than bromine. We want it more. It's closer to fluorine. In fact, oxygen is number 2 on the electronegativity chart. And so we wouldn't create another double bond. If we create another double bond, then that would throw the negative charge on bromine. Oxygen would go to 0. We have to have a negative charge here because this whole thing's an ion, the bromine ion. And so what should we do? Should we expand the octet? First off, is it possible to expand the octet? Yes, it's possible because bromine is a third shell or third period element. Second ones don't. So chlorine would never expand the octet. Sulfur, actually these would. This is fourth shell. Third could expand. Second will never expand. These will never expand the octet. There's a reason for that quantum mechanically.
So that structure would be more stable than that previous one?
Let's take a look. ZrO3 minus. Take a look at some structures for bromine here. When you look at the structure for bromine, this is not a good structure here. It's a trade-off, we have to look. So for example, if we leave it, well, let's just look at some different examples. We want to see different examples of bromine. What did they do here? They formed 2 double bonds here and 1 single bond, but they are using dots. This is what we got there. If you form 2 double bonds, actually this is showing forming 2 double bonds here. So if we leave it as an octet like this, there's a +2 formal charge on bromine, which is kind of high. If we make 1 bond, then that goes from +2 to +1. This is still +1. We can form another one that brings it to 0, 0, 0, 0, and then -1 there. So this is what showing why 2 double bonds might be good. If we form 2 double bonds, well, anyway, we can also have resonance formed, depending on where we put the 2 double bonds. Okay, this one is showing all single bonds. Two double bonds, all single bonds, 2 double bonds, 2 double bonds. It's different ions. This is not good here. Why is that not good? This structure is not so good because this particular structure would mean that all the oxygens, what would the formal charge on all the oxygens be? 0. And the formal charge on bromine would be, well, bromine has 1, 2, 3, 4, 5, 6, 7, 8. Bromine's supposed to have 7, so it's minus. So that throws the negative formal charge on the bromine for those structures. here they're showing 2 double bonds. Here they're showing that the negative formal charge on the 2 double bonds is on the oxygen. So they're saying this is the best, but if we do 3 double bonds, then it throws a negative formal charge on bromine. Don't want there. 2 double bonds on bromine. No, it's not that you can trust this. You know, this after all, people can put anything on the internet. It doesn't have to be peer reviewed. But what would you say the majority of structures are online? 2 double bonds or all single bonds? 2 double bonds. Now, when we have 2 double bonds, we have a choice for resonance. These are resonance forms. So when you do resonance forms, you leave the atoms fixed. You never move the atoms. So I'll never move this oxygen and move it down here. We leave the atoms fixed and then see how many unique arrangements of electrons we can have. So if we let the atoms fixed, then I have the, let's say we'll say left and right. That's one unique arrangement. Another unique arrangement would be up and right. And another unique arrangement would be up and left. Are there any other unique arrangements of 2 double bonds? Can you think of another arrangement that hasn't been done?
Down to the left, down to the right.
Well, there's no down because there's no atom here. So we can't have a down in this case.
But you could write it that way, right? Or the
No,
same thing?
we never move the atoms. You have to leave the atoms in position. So if you made a double bond going down, what would it go to? If I made a double bond going down here, it would be going to nothing. The oxygen's up here.
Well, then you need to put the oxygen on the bottom and not on the top.
We can't move the atoms. You have to, if you start moving the atoms, then you're in for a headache. You have to leave the atoms in position and then just look at how many unique arrangements of electrons there are. But if I start moving the atoms, then I'm going to have all kinds of things. Like, for example, I can move the atom up, right, and down. Then I could just keep rotating it, but it doesn't, you gotta stop it rotating and then look how the electrons, it's electrons. It's not how the atoms can be positioned. And so there are three unique arrangements of 3 resonance forms for bromine. Now, what are we going to do? Well, it gets a bit complicated. And so what we're going to do is this. We're going to say that this is okay or that. And so you could write either. The reason I bring it up is your book is just going to leave it as octet, like this. Your book doesn't even bother with formal charges. And so it comes up with this structure. Everything has an octet that's good. And so the reality is that there's going to be some kind of minimization of the formal charge. Actually, both of these pictures there are problems with when you get into the bonding theory more advanced level, but we'll go with either. So we come up with situations, different scenarios that come up. And so one of the things that comes up are these two, BF2 and BF3. So let's take a look at BF3 first. If we look at BF3, Boron has 3 electrons, and fluorine 7. We have 3 of them, so 7 times 3 is 21 electrons. So altogether, we're going to have 24 electrons here. And so we'll make some kind of structure, maybe like that. A boron with 3 fluorines attached to it. And then we'll complete the octets. Yes. By drawing pairs of electrons. And so now everybody has an octet in this structure, which is good. And so what do I do next? What's the next step? Count the electrons. So we're going to count it. 2, 4, 6, 8. So this is 8 times 3. It's 24, 25, 26. There are 26 electrons in this structure. There are 26 electrons. That means I have to, I have too many. So I have to take away 2. So who should I take them away from? Fluorine or boron? Boron. I should take them away from boron. Why? Because fluorine's more electronegative, so boron's going to be easier to remove the electrons from. Now I'm good. That makes 24 electrons. But there's a problem. The problem is this. Does boron have an octet?
No.
Boron does not have an octet. Well, that's easy to fix because in that step 4, all we have to do is form a double bond. Let's try to form a double bond here, or a multiple bond. And so what I'm going to do is I'm just going to take a pair of electrons and bring them to the bond. Okay, now that's good. Everybody has an octet, right? And we'd be done with step 5, but then I added that step 6. What is that step 6? We got to look at the formal charges. And so tell me what the formal charge on this fluorine is here. 0. This fluorine? This fluorine? This fluorine's going to be plus. And this boron? Minus. What were the formal charges in this structure? This is 0, this is 0, this fluorine is 0, and this boron is 0. All the formal charges are 0. So essentially this is what's happening. In order to give boron an octet, fluorine has to lose an electron. Lose an electron to sharing. That lone pair used to belong entirely to fluorine, but now it's going to be a bonding pair. The bonding pair has to be shared. And so it's losing an electron. And so in other words, fluorine is giving up an electron to boron. Fluorine is giving up an electron to boron, but take a look. What's electronegativity of fluorine? Fluorine's electronegativity is a 4.0. Boron's electronegativity is only 2, so there's a difference of 2. Is boron strong enough to pull an electron away from fluorine? No. In fact, this is not going to happen. Fluorine is, no matter what fluorine's bonded to, fluorine is never going to give up a lone pair to form a bonding pair. In other words, this doesn't happen. This is the correct structure. And the reason is because fluorine is too selfish, or fluorine has too much attraction for the electron. Fluorine only forms single bonds. You'll never see fluorine form a multiple bond, because in order to form a multiple bond, it's going to have to lose electrons. And it's not going to lose electrons because it's too powerful, it's too electronegative. And so this is the reason why we have this situation. This situation is when we have less than an octet. And so molecules with less than an octet would be BF3. BF3 is going to have less than an octet because fluorine cannot double bond. The same thing with this. For BEF2, I'd like this fluorine to donate one pair, this fluorine to donate one pair. So I have a double bond, double bond. But if fluorine were to do that, then this fluorine would go to +1, this fluorine would go to +1, and beryllium would go to -2. You think beryllium, there's no way beryllium's strong enough to pull 2 electrons, one from each fluorine. And so these ones will have to suffer with less than an octet. And we just cannot make an octet. That's fluorine. You know, fluorine's peculiar in that way. But let's take a look at another molecule. Here. Let's do carbon monoxide, CO. Why don't you come up with the Lewis structure for carbon monoxide?